And now, the official welcome to the lecture. Sorry for the minor delay. Once again, a super happy and positive lecture that's coming ahead now. It's a little bit the preparation for Anand's lecture next week. Short heads up, we learned from our mistakes last week. So if I'm not mistaken, next week is a MOOC session, but we'll meet for the exercise at the normal lecture time. So 1:15, you watch the stuff at home. At 1:15, we meet for the exercise stuff. Then we have more than enough time, and those people who come here to do the math session at Digit don't have to wait forever. So I think we can maybe fix two problems at the same time here. Good. So next week we have so-called life cycle assessments, where you try to figure out what's the environmental impact of any given product or service that you use. So what's the environmental impact of me drinking a coffee? How would you quantify that in numbers? It's next week. And today we're having a little bit of a broader view with respect to the resources of those planet and what it can take. We've looked into this like a little bit in the intro slides when we talked about planetary boundaries, or this like Earth overshoot day, where you essentially had a very rough understanding of, yes, we used too much or too many resources and polluted the environment too much or too little, but it was essentially just for each and every year just a column that says green or red. Now we're trying to make it a little bit more detailed for the whole planet, and then next week for specific products, so that you, for example, could make a justified statement about the question, what's more sustainable, a internal combustion engine car or a battery electric vehicle or H2 or whatever. So that's gonna be the next 2 weeks. Minor news and updates. We finally have so everything stays the same, it's just essentially like providing you more detail. The invited lecture that we planned for the 22nd of January is gonna be provided by Gabriel from the cat farm. He's been here last year with an intro to the cat farm and some insights. This year, he's going to give a speech or a lecture on power and balance, horizontal governance for collaborative communities. Everything else stays the same. It's just like more details than we've provided before. We also had a little bit of feedback for the exercise sessions, but we'll get back to that in the Q&A session, exercise session, because I'm already late and we have to catch up a little bit. So we'll get back to that. So now the intro to today's topic. In extremely simple terms, our planet is not really much more than the sandbox. You have a finite planet, you have a finite system that has a certain set of resources, like in this case sand, and that can take a certain amount of environmental pollution, like children peeing in that sandbox, putting plastic there, whatever you like to call it. And if you explain that to a child that if you throw out sand left and right, you won't have any sand left, or if you dump all your trash in there, it will be very dirty, that's quite simple. And I guess most grown-up people also understand that analogy, but no one really acts accordingly, or just a very small minority acts according to that analogy. And we've seen this in the Earth Overshoot Day. We use, in 2027, we acted like we have 1.75 planets, despite the fact that we only have one planet, and it only got worse since then. And you can now approach that topic from various angles, but since I'm a computer scientist, Anand is a computer scientist, a lot of you are computer science related students, even though not all of you, the maybe intuitive way could be via equations and math models, because that's what computer scientists and especially mathematicians like to do. Who's familiar with Lotka-Volterra equations? Predator-prey equations? Something about rabbits and foxes? Not a problem, just curious. Good, so Lotka-Volterra equation, super simple. You have a population of a predator, in this example blue, being foxes, and you have a population of prey, in this case rabbits. And since fox like to eat rabbits, there is some kind of a connection between the population of both. So a lot of rabbits means that the foxes are like great, amazing food supply. So the rabbits start to decrease while the foxes get more and more and more because they have perfect environmental conditions. So the population growth. The more foxes you have, and I'm not quite sure if foxes is the plural of fox, but we'll take it for now, is causing a decline in rabbits because more and more foxes eat more rabbits. At some point, there are not enough rabbits left to sustain the fox population. So the fox population also declines. That means less fox. Rabbits can recuperate under the assumption that there is still like at least 2 rabbits that can continue the population cycle remaining, and preferably a male and a female rabbit. And then the whole cycle starts again and again and again. This is, of course, a super simplified model. It leaves out all other conditions. It only accounts for foxes exclusively relying on rabbits as food. It doesn't account for environmental pollution, humans hunting foxes, foxes being crashed by cars, and so on, but you get the idea. So the overuse of a certain resource by an ecosystem participant will cause a decline and then can even cause the entity that overuses a certain resource also to decline or collapse or crash, depending on what type of word you would like to use. And now we're gonna take this to a higher and more abstract level and think about this in terms of this planet. And this is not really a new idea. People have done this for at least 50 years, and this book that you're looking at right now is, on one hand, in parts the cause for the name of this course, because the English translation is The Limits to Growth, and also one of my first contact points with that topic. I'm not 100% sure when I first read that book, but I think I stumbled upon it when I was like 13, 14, 15, something like that. And it first sounds like a super boring scientific book, but it's quite nicely written and you can easily read it. And the people in that book essentially tried to model, given the assets of that time, the world in terms of resource consumption and some other parameters, and trying to predict where the world is going and if we're on a sustainable path. They didn't use that word back then, but can we sustain existing as we do right now, or is there potentially a problem? And please keep in mind that they did this on machines using computing power that is probably less than this weird USB presenter. Maybe it's slightly more, but you get the idea. So there's not really much computing power there. So it was a very rudimental and simple model. On the other hand, quite powerful. So one of the conclusions of that book, one of many conclusions of that book in 1972 was, if the present growth trends in world population, industrialization, pollution, food production, and resource depletion continue unchanged, the limits to growth on this planet will be reached sometimes within the next 100 years. Statement from 1972. The most probable result will be a rather sudden and uncontrollable decline in both population and industrial capacity. So in more scientific words, what I've just explained to you using the sandbox example or the predator-prey equations from Lotka and Volterra. If we continue to overuse our sandbox, we'll be fucked. And the most prominent and most commonly known figure from that book is displayed here. It's a so-called World 3. World 3 is the model that they created, standard run. And you have the 5 resources that already showed up here in the text version listed there. You have a set of resources. You have food per capita, so food per person. You have the overall population. You have industrial output per capita, and you have pollution. And you start with a fixed set of resources at the top, which is just the assumption, okay, how many resources do we have left based on 1972? And you have a given set of population. and you also have the industrial output per capita, the food per capita. And since this was 1972, or they did it slightly before that, you have also some historical data. So the first part is essentially historical data, and then from 1970, 1971, 72 onwards, they go using the modeling approach. And what happens? If you follow the trajectory of population growth, you use more resources. While population is already growing, you also have an increase in living standard, which means more food being available per person, industrial output going through the roof, but also consumption of these industrial goods, and producing all of that and making sure that this is available causes pollution. And the World 3 Standard Run essentially predicts a peak of population caused by resource depletion and environmental pollution. Because we can't grow indefinitely, as we do right now, in a limited, finite system. So when I was young, we had like something like 5-6 billion people on this planet. Now we're closing on the 8 billion, or maybe even crossed the 8 billion. We're not slowing down, we're rather going towards the 10 billion. And you can't just use more resources, because at some point you're running out of resources, you can't pollute the environment any further. And given this finite set of constraints and resources, you can also easily see that not everyone can live on the standard as, for example, people in the US or other like first world countries without causing some serious environmental problems. So 1972, quite simple prediction. You can also like say this is very intuitive, but they created a model with underlying equations governing that model that gave this a mathematical and scientific foundation. They also published some updates on this book. There is the 30-year update, and I think there was also a more recent version a few years back. And in the 30-year update, they essentially looked back at what they predicted. They also tackled some of the criticism that they received. We'll get back to that a little bit later. And essentially check, okay, how accurate are our predictions? Bad news, quite accurate. We left you a few links to play around with that model, because it doesn't make too much sense now if I play with the model in front of you. So you can just click on the links. They both rely on the underlying World 3 model. The second link I think is slightly more complicated, but also gives you more insights into the model. The first one is quite simple. You just move a few buttons left and right, and then you can play with different assumptions and see what the results according to the World 3 model are. Which now leads us again back to the planetary boundaries that we, if I'm not mistaken, briefly touched in the intro slides before we continue with the World 3 model. Because the planetary boundaries are slightly easier to understand, unfortunately, therefore less accurate and not as expressive as the World 3 model is. So the concept is quite recent, was introduced by Johan Rockström and his team from the Stockholm Resilience Center. Rockström is now one of the two directors of the Potsdam Climate Institute and continuing the work on this. And the idea was essentially to quantify planetary boundaries within which future generations can continue to exist. So very closely linked to the sustainability definition that we had, making sure that our needs are met without compromising the needs of future generations. And they tried to find indicators that on one hand they can quantify, and that also seem to be the most relevant indicators to make statements about the planetary boundaries, because not every indicator is as important as the other ones. So some are more important than others. So they had to figure out what are the relevant indicators, and then how do we quantify each indicator. So like CO2 measurements in the atmosphere being an indicator, and also rather simple to measure. You just put a lot of sensors in the atmosphere and then measure what the CO2 level is. Others that we'll get to, like ocean acidification, more difficult. And initially, okay, maybe before we go to the initially, crossing that boundary means we are close to being fucked. And those are the 9 indicators that I found. Biosphere integrity, climate change, novel entities, so something like PFAS, the stuff that you use, also chemical components, something that is usually used to make pans not stick to food, but being essentially stuff that doesn't degrade in the environment and is very nicely consumed by your body and then not leaving. Stratospheric ozone depletion, atmospheric aerosol loading, ocean acidification, biochemical flows, freshwater use, and land system change. Totally fine if you don't have a perfect understanding or intuition what all of them means. That's not the point here. The relevant point here is which of those indicators are already beyond the safe zone where we should operate. And initially, in 2009, when they introduced that concept, they were only be able to assess 7 boundaries because they didn't figure out how to quantify those boundaries. So they could only make statements about 7 of them. And they noticed 3 of them are already crossed. Biosphere integrity, climate change, and biochemical flows already being crossed. They did not have an idea, for example, how to, or they had maybe ideas, but they couldn't provide numbers, for example, how to measure ocean acidification. Next update 6 years later, better numbers, better ways, better methods of getting more precise information. Now we're at 4 crossed boundaries, so land system change joining that group where we do more harm than the planet can take. And then finally last year, all 9 boundaries assessed and 6 of them already crossed, with another 1 being close to being crossed. There is one that seems to be extremely fine, which is on one hand a good sign, even though it's maybe leaves a bad message, but the ozone depletion seems to be doing quite well. Anyone got an idea why? Why don't we don't have a problem with the ozone layer? Exactly. We banned the stuff that damaged the ozone layer. So we've been in a similar situation before, and we managed to do something. So whenever you get arguments like, yeah, I would like to do something about climate change, environmental pollution, or saving our planet, but it doesn't matter if I do something, everyone has to do something. Yeah, sure, but there was also one person who started this ozone layer discussion, and we somehow managed to fix it. So the ozone layer is now doing quite fine. That doesn't mean that we should put all our trash there, but you get my point. Good, so take away from the planetary boundaries. They are a concept that focuses on 9 specific indicators to give us an idea where we're standing with respect to stressing our planet. 6 of the 9 indicators being already crossed, so that means we're operating in a zone that is not safe for the continuous existing of humanity. And the 7th one being close to being crossed, which is ocean acidification. Yep, that's what I already said in that one thing before, so sorry for racing ahead. Good. Minor update from 2024, slightly different representation of the same factors or some more factors, but with a slightly more precise labeling on where we are going. So, for example, for the stratosphere, the ozone depletion, we're not really moving left and right. For aerosol loading, we're still in the safe space and even slightly decreasing it. And here you can get the idea for the others. So the more arrows to the right mean increasing, more arrows to the left meaning slightly decreasing, no arrows left or right mean we're somehow in a stable position. And you can see that all the 6 that already have been crossed, 1, 2, 3, 4, 5, 6, 7, 8, okay, slightly more, indicators here are heavily moving in the direction of increasing as a problem, which is in the field of climate change, mostly being linked to CO2, like a good example. We know, and we talk about this more or less on a daily basis, that we need to reduce CO2. Still, we just had a record emission in 2024 when it comes to CO2 emissions. We're talking about it, but we're not doing much. And the same is true for most of the other indicators. So the one that is not being crossed yet, heavily moving to the right, meaning we're getting into an unsafe area here. Good. That just being a short detour to those planetary boundaries. Now back to the limits to growth, to the 2 books, and to the underlying model. So I already mentioned The underlying model is called the World 3 model. And the book was published in 1972, but the journey towards that book and towards that model started already in the 60s as a guy called J. Forrester, who developed something that is called systems dynamic. It's a methodology and a mathematical modeling technique that you can use to build something like the World 2 or World 3 model. And it is used to understand the nonlinear behavior of complex systems over time. So linear behavior being, if I buy one piece of or bar of chocolate and eat it, I consume 500 calories. If I buy 2 bars of chocolate and eat both of them, I consumed 1,000 calories of chocolate. And it's a linear thing. Other equations might not behave in a linear way. And this is where system dynamics becomes a tempting tool of choice, let's phrase it like this. Forrester initially created it or used it to create the World 2 model, so the predecessor of the World 3 model. But that's not our main focus tonight or today. And he spent quite a lot of time in the process of modeling and creating the system dynamics approach. And system dynamics starts with defining so-called levels and their rates. You could also say stocks and flows. So I have a stock of coffee here, and the flow rate essentially is me taking zips from it and thereby consuming a certain amount of that stock over a certain period of time. Unfortunately, quite linear in this case, but you get the idea. There are also so-called laundry lists that specify the set of influencing factors for each of the rate variables. So when you think about death of people, then, for example, the availability of good healthcare is an indicator that influences how many people die per year. No healthcare, more dead people. Less amazing healthcare, still dead people, but less. Oh. So levels could be, or levels are in that model, population, and there's an inflow parameter for the population, which is the birth rate, because that's what mostly influences how many people we have, and outflow being deaf people. Money, similar example, inflow is your income, outflow is your expenses, what you have left in between, what you're not using could be your stock. If you're overusing, your stock depletes. Laundry list for birth rate, just as one example. There are many, many, many laundry lists in that model, but taking one to give you an example. What influences the birth rate? So on one hand, the population. The standard of living, you're more inclined and happy to have children if you're not struggling for survival every day. The food quality, very similar to the standard of living or part of the standard of living. The food quantity, education, the availability of contraceptives. Not a complete list, but you get an idea what that laundry list entails. So now, that's system dynamics. This is what it can do, or that's the rough basics that you need to understand today. And now let's move from World 2 to World 3. So Forrester created this World 2 thing, and then a non-governmental organization, NGO, called the Club of Rome, invited Forrester to apply his ideas to the global economy and ecosystem. Forrester wasn't really into that and declined and proceeded with his project without the Club of Rome. But one of Forrester's former students and colleague, Dennis Meadows, organized the project for the Club of Rome. So he's, together with his wife and another, like a team of fellow researchers, essentially the people behind that World 3 model. 17 researchers spent a year refining and enlarging Forrester's World 2 model, which then was called World 3. Considerably more complex, but also more powerful. So it gives you more predictions, but also better predictions. And this is a super simple representation of the different components of the World 3 model. You already got them from the text statement that I read you, but also from the figure that I showed you. So the 5 key components here are population, agriculture, industry, resources, and pollution. Agriculture and industry then being placeholders for food per capita and industrial output per capita. So in those different components influence each other in either positive ways or negative ways. So More food means more population, less food means less population, and so on and so on and so on. You get the idea. The overall final model then consists of 150 equations that influence each other and govern the whole model. The 5 main sectors we just covered, and the simulation period that they tackle is going from 1900 to 2100. Very important statement here, especially if you go and look back at the figure. It is not time sensitive. Just because the collapse seems to be somewhere in the 21st century and you can try to extrapolate, okay, this is 2040 or 2050 or 2060, that doesn't mean that the collapse will happen 2040, 50, or 60. It's a model, it's not time sensitive, it's not what it's made for. It gives you an overview of what's gonna happen, but it doesn't tell you exactly when it's gonna happen. So please don't try to deduce whether it makes sense to finish this study degree or not. Make that, please, based on the overall course and not just on the World 3 model. Yeah, just like for curiosity, it's written in a language called Dynamo, but that's not going to be exam relevant. So let's start with the 5 components and specifically population. So what do you model in a population? You model people. You have control mechanisms that influence the population, birth rate, death rate. Maturation is also a part there. Because you have to carry people from one age category to the next when you simulate them. Usually 5-year-old children don't contribute to the population in terms of reproducing further children. Similarly, 60-year-old people also rarely get children, so you get the idea why it's also important to move people from one age category to the other. You also consume more resources or less resources, and so on and so on. Death rate probability gets higher the older you get, and so on and so on. Agriculture, being mainly concerned with farmland, arable land that you can use. Some land is very productive, other land is less productive. Soil degradation over time causes arable land to become less productive. You also have some factors like desertification, groundwater being used up. So there are like different factors that concern or that influence how much arable land you have. Control mechanisms are cultivation of new land, which is something like where, for example, you burn down the Amazon forest to plant palm oil trees there, but you also can't do that forever because at some point you won't have any Amazon forest left anymore, so you can't burn it down. And then there's mechanisms like farmland lost due to erosion. Urban development also happens a lot, that what was previously farmland now is a shopping center. There are different factors that go into the availability and productivity of arable land. Industry being mostly represented by capital that is a proxy for factories or productive facilities, so everything that contributes something. And the control mechanisms are quite simple here. Investment in and outflows, so inflows being people putting money into building a new factory, outflows being something like depreciation, because even if you have a brand new factory, over time it depreciates. And when you now have all the components and then try to run the simulation, you will, and especially also interpret that simulation, you will get into a dilemma, which they called Forrester's dilemma. Let's say you start here, so this is historical data, and here you start your simulation. What happens in the very near future is pretty simple to predict. I could, for example, now predict that I will shout at someone of you, which I can easily achieve by then shouting at you. Or I could drop this, or I could predict that one of you will fall asleep during the lecture. Like there's a pretty high probability that I can correctly predict this. But the more or the further you go into the future, the bigger the range of events and predictions that could happen will get. The problem is the near-term future, what happens in the next 5 seconds, is not as interesting as what happens in 50 years. Like you probably don't really think hard about what happens in the next 5 seconds. But you might think about, okay, what will my life be in 5, 10, 15 years from now? But it's getting more and more difficult to make an exact prediction because you have such a big range of things that could happen because so many factors influence each other. And that's pretty simple Forrester's dilemma. So one can forecast future conditions in the region where action is not effective, and one can have influence in the region where forecasting is not reliable. So let's get to the simulation results. There are 4 popular scenarios, and each of these scenarios has different underlying assumptions. We already talked about the so-called standard run, which is also called the business as usual scenario, where we just continue as we did when they created that model, which is astonishingly accurate. And you have seen the results in the previous slide. So we had a fixed set of resources. We started with a certain level of population, food per capita, industrial output per capita. And the more people we get, the higher the food per capita, the industrial output per capita, the more resources we use, and the higher the pollution. And at some point, there is a drop in the population. So long story short, a collapse due to natural resource depletion, which is the main driver here, pollution being a problem, but not the main driver why everything goes south. So now let's assume more resources, because maybe we haven't discovered all the resources yet, because they still find new oil fields or new resources that you could mine that no one knew about in 1972. And probably find new oil fields for a few more years, even though they're more difficult to extract, but that's a different discussion. So let's assume we just have double the amount of resources. Because if we're now collapsing due to resource depletion, let's just assume we have more resources, either because we find more resources or we recycle more stuff. Like both pays into having more resources. Let's see what happens then, which is then the business as usual 2 scenario. So double the resources, start pretty simple, but we have extremely steep curve for industrial output because we can just produce so much more with more resources. Highly correlated, increase in population and also food per capita, but we're still depleting our resources because we're just using so many, and we also have a new problem here. Increasing and maximizing industrial output also causes pollution to increase and makes it go through the roof. So just having twice the amount of resources, or even there are like scenarios where they just assume unlimited resources, doesn't fix the problem, because then one of the other factors will bite us in the ass. So now we have a collapse due to pollution, which could be literally like environmental pollution, could also be climate change. Please think back, this is 1972, climate change wasn't a big topic of discussion there. So factors that make our environment difficult to live in, essentially falling into this condition. So okay, what's the next logical step? If we die due to pollution, then let's assume and make sure that we develop technologies that are targeting this problem, like trying to carbon capture or to not have any environmental pollution in the first place, and then also make sure that we adapt those extremely fast, because as you can see, it's an urgent problem. So that's the so-called comprehensive technology scenario. So we build on the assumption that there's twice the amount of natural resources, and we also build on top the expectation that we have exceptionally high technological development and adoption rates. And what happens now? Once again, resources deplete a little bit, but not as much as before. Population grows, food grows, industrial output grows, and there is a certain dip here in the food per capita part, where we have a problem with pollution, and there's also a minor decline in population. But we somehow manage to get somewhere, but we have to live with a lower industrial output compared to the max peak that we had before. So we're slowly getting somewhere. However, the rising cost of technology eventually causes declines, but not a total collapse. Because just catching essentially you're trying, it's easy to get the low-hanging fruits of environmental pollution, but the more you produce, the more you influence the environment, the more also minor contributions to environmental pollution become relevant. So if you essentially stop putting like industrial industrial wastewater into a river, like you just stop that, it's quite simple. But if you then at some point have to like take care of every gram of pollution that comes into the environment, it starts to getting increasingly expensive. And this is also true with respect to climate protection, climate change related activities. The later you start and the more you have to do, or the more comprehensive you have to do it, the more expensive it gets to just catch everything. That's why it would way more economic to just stop emitting CO2 than having to make that effort to get it back out of the air. Good, so we somehow stabilize our population, we somehow stabilize our standard of living, but we're not quite there yet. The last scenario is yet another iteration on top, yet another assumption, where we say, okay, instead of just trying to solve that problem from a technological perspective, we also change values and priority of our society. So maybe instead of needing or wanting a new iPhone every year, we are fine with that phone that we have as long as it lasts. And that it might become sexy to have a phone repaired instead of buying a new phone, or having second-hand clothes instead of going to a fast fashion shop every other week and getting new trash. So let's assume that. I know, quite radical, but let's assume that. What happens? Then we get the so-called stabilized world scenario that looks quite stable. So a lot of lines end up being flat, and there's still like overuse of resources, but you're almost getting parallel to the x-axis, and pretty much pollution problem resolving itself over time due to the society value change and priorities, as well as the comprehensive technology and adoption rate that we inherited from the previous models. And I think now it's time for Anand to already prepare a survey. Or is there someone online? Yeah, then maybe that person online can send his vote to you, or his or her vote. But I think now we're almost there, where we have a voting up for you. So essentially, the result here is population stabilizes in the 21st century, as does human welfare on a high level. Please keep in mind, we have made a lot of assumptions to get here. Twice as many resources as we're aware of, comprehensive technology development and adoption rate, and a change in societal values and priorities. So what does this model now tell us? It indicates that we are already consuming resources at a faster pace than the planet is able to regrow or generate. You now already have an intuition for that, because I'm annoying you with that fact for the last 4 or 5 weeks now. But in 1972, that was even more unpopular as it is today, because it's a time where industrial revolution reached its peak, where people after the war got increasingly involved in industrial production by being employed there. Like, everyone had a really great time in the 1970s, 1972, and suddenly there's someone that says, look, if we continue like that, we might get a problem. Like, you're extremely unpopular with that opinion. But for you, it should be not big news now. Standard of living, not sustainable, you already seen that. And the relieving limiting factors are not really solutions. So assuming twice the amount of resources, or just assuming wildly unrealistic technological advancements and adoption rates, they are more accelerators towards disaster. So just having more resources doesn't solve your problem. And preventing the worst case scenario by reducing consumption is probably one of the easiest quick fixes that we can attempt to buy us more time, to shift this drop in population and drop in living standards further to the right, and maybe even avoiding it in the long term. So that leaves us with the question, where are we now? So we can now choose if you all want to log in, or if we just do a vote by hand. Vote by hand? 2 people? What is it now? Vote by hand? Vote by PC? Okay, vote by hand. So who thinks we are at option A? The scenario that we are in right now resembles more option A than any other. 1 person. The person online, please send the result to Anand. Option B? Wait, did you raise your hand for option A? Yes. So 3 for option A. Good, okay, 3 for option A. Option B? No one? Option C? Are you sure that you all want to vote for option D? Because I got 3 votes out of 1, 2, 3, 4, 5, 6. Like, where are you standing here? Option D? 2 people for B? 3 people for B? B. D. You're very optimistic. Okay, so come on, guys and ladies. What's your guess? A, B, C, D? So D, A, D, A? A? So, okay, so you have 4 for A, 2 for B, 1 for D. Anyone lost? Okay. I like your pessimism. So the answer to that is, right now we're very close to B. And like some aspects pointing towards C, so it's not a quite simple answer. But unfortunately, I mean, the D option is what we should go for. But if you have been outside or read the news, you might have noticed that we're not really there. So we neither have exceptional adoption rates for technologies that save our environment or combat pollution. We definitely not adopting them at a fast rate. And the shift in societal values is also something that I'm still looking for very much. So this is definitely where we should go for, what we should do. But right now we're more like B, maybe like minor parts of C in there. Which means we're fucked. So this is a model that has been around for 50 years. We received some minor updates after 30 years, but it left people at least 50 years. That left them 50 years to come up with criticism. And a lot of the criticism already originated quite rather recent after they published the paper. And would be unfair to just present you the model, tell you it tells us it looks bad, and then not like give you all the downsides or the criticism of the model. So let's do that as well. The model, as every model, has limitations. So whenever you try to capture the real world using a model, you have to make some sacrifices. Even if you just want to model the existence of those few people here, you cannot capture the full existence of the people here in that room. You can try to categorize them by height or by describing their parameters by height, by weight, by age, name, and other parts, but you won't be able to come up with a comprehensive model of each and every one of you. Just like even if I give you the task of modeling one single person, you would run into like difficulties doing that. Even if I ask you to create a model of just this presenter, you would need at some point to make limitations based on certain assumptions that you have to make. So that's like always a model. So I think my chemistry teacher loved to say like every model has its limitations, and also that means that in some parts it's quite good. It describes certain aspects very accurately and very good, but it sucks describing other parts. So even the model creators said, yeah, okay, this model has downsides, so we're aware of that, but we still think it holds true. So even the creators are not quite happy with the whole thing. There is even a complete book that is longer than the original book, criticizing the Limits to Growth book. It's called Models of Doom. And the 1972 book also did not contain the equations governing the model. So they presented the results, they presented the simulations, and they discussed their findings, but they did not, as we would say today, open source the underlying model, the underlying equations, but they finally did this 2 years later. So that's why we now have like quite a good idea how it works, and that we can replicate it again and again and again. The most prominent critiques came from the economy people, because telling an economist, hey, like infinite growth doesn't work in a finite system, makes you extremely unpopular with them. I studied banking and finance before I became a computer scientist right after the financial crisis. Asking them why we had a financial crisis and if it maybe has something to do with limitations to an economic system that can't work on infinite growth not very popular. So they are not happy with this because the model essentially questions the fairy tale of eternal economic growth in a finite system. So with limited resources, how can you have infinite growth? You can try to create growth by shifting to like some kind of service sector, but even that service sector consumes resources, so like you're getting into like arbitrary arguments there. A more valid criticism is the fact that they used aggregated variables. So we had, when we talk about resources, we did not differentiate between water, iron, sand, and so on. We just had one resource, one food, one pollutant, and one population. On one hand, due to the fact that we're talking about 1972, where they had the computing power of a calculator, and also the fact that you need sufficient data to rely on not aggregated variables. So if you can clearly define for each and every relevant resources the number, then you can work with those numbers. But if you don't have that data, you can't differentiate between them. And once again, please keep in mind, 1972, they didn't have Google, they didn't have ChatGPT. Getting aggregated, getting proper separated numbers for those resources, or even any of the other components, was quite hard. It's quite hard today to get accurate numbers on that, but 1972, forget about it. So it's a valid criticism, just an explanation why they made that decision. They also choose to not have any geographical structure and no social distinctions. So there is something like an average food per capita. Once again, same reason as I gave you before. Something that they could have tackled is a lack of statistical analysis, which means, for example, no error bars. They give you the model simulations and the graphs, but for each and every data point, they don't give you, like, for example, ideas of what's the rate of error for each of those. Like, they think it goes there, but it could also, with a certain probability, be there or there. You don't have any statistical analysis for the data points that you get. And funnily enough, they have been, on one hand, being accused of being too complex, 150 equations, who's supposed to understand all the implications that they have among each other, and on the other hand, of oversimplifying stuff. Both being true in certain aspects, but it makes it quite hard for you as a scientist to fix that. No pointer anymore. And that already leads us to the conclusion part of this part. We'll have a live seminar part later on. But what's the main takeaway that you should remember from this session? So first, the concept of the planetary boundaries, 9 indicators that are supposed to help us, or that help us to tell, okay, first of all, like, what are these 9 indicators? Trying to find these most critical indicators that give us an idea about our planetary boundaries, then quantifying them, and then telling us, okay, where did we already cross the line, which then translates to us being in an unsafe space with respect to the continuous existence of humanity. And then the World 3 model, where we had different scenarios. The most famous standard run that everyone knows, who has been around in 1972, and then the different assumptions that lead to the different predictions for the future. And I guess we agree that the stabilized world model might be a good goal to pursue, and not all the others where population collapses. And please also keep in mind that there's widespread criticism for this model, like from different angles, but all of that criticism still, despite all that criticism, still the main message holds. Like, you can criticize them on how they did the model, what they assumed, but like, even if you change this very drastically, you still get to a very similar result, and it's also extremely intuitive. If I go back to the sandbox example, unlimited resource consumption in a finite system doesn't work. So that's it for this session. We will provide you further resources that you can use to go deeper into this. So the original book, the 30-year update, the equation book, also Freeman's book, Models of Doom, quite entertaining. And then the website for the planetary boundaries, and also the most recent planetary health check both super interesting. And Brian Hayes providing some nice thoughts on computation and the human condition. Can also highly recommend that link. That's it, I would say. 5-minute break, and then we meet again for the offline part, where we're first gonna go through a little bit of feedback for the exercises, and then have a live session, which we are not gonna record, but might be still interesting to join. So thank you very much. See you all in 5 minutes.